In this video, we discuss mathematical concepts behind machine learning. Recall that in supervised learning, the goal is to find a mapping or function, and we call this f, that allows us to relate inputs to outputs. We show outputs using x. Here it can be a vector in general that belongs to some space curly x, and we want to map this to our outputs. To understand this, let's look at one of the examples that we had before. In the case of regression, we wanted to relate years of experience, and this is our feature or our input, to salary, which is our output. And therefore, the goal is what kind of function f we have to find so that for any new instance, we can predict the salary as accurately as possible. And as mentioned earlier, the main thing in machine learning is that we need to have data. And data comes in the form of input-output pairs. So therefore, you can see that we have these pairs of inputs and outputs, and we use this small n for indexing, and n goes from 1 to uppercase n. Therefore, uppercase n is the sample size or the number of observations or the number of instances that we have. And in a simple case, especially when we have tabular data, we can think of the number of features or the dimensionality of this space as being D, meaning that this X is in RD, where R is the set of real valued numbers. Now, in terms of the outputs, it really depends on whether we are working with classification or regression problems. In classification problems, because we have categorical outputs, and if we have more than two classes, it's very common to label them as 1, 2, up to C. But remember, these numbers here, they don't really have any numerical value, and these are just some numbers to differentiate between different classes. So meaning that if I really want, I can call these classes 0, 1 to C minus 1. Or I can multiply each of these by 2 and say this is 2, 4 to 2 times C, right? So as long as we have C distinct numbers, that's the key point behind classification. In the case of binary classification, which we focus a lot in this course, we can have multiple notations. So it is common sometimes to use the labels or categories as 0 and 1, and sometimes we use -1 and 1. And in this lecture, you're going to see why this really, we have these different notations because sometimes it's more convenient to use one over the other one. But overall, it's exactly the same idea because we have two different classes, which means that we need to have two different labels. And these labels do not have any numerical value because we are not really trying to measure the distance between, for example, 1 and -1. That's what we mentioned, that finding the distance in classification problems is always a challenging problem. And we're going to see some examples of that. So with that motivation in place, now let's talk about one of the most important concepts in machine learning, which is this idea of empirical risk minimization. Okay, so to understand the empirical risk minimization, let's start with what we know. So we have a data set which we showed that using D, and this contains these input-output pairs. So this is our first observation that we have. Then this is our second one, and we have xn, yn, and for simplicity, we can just index this using small n, where n goes from 1 to uppercase N. When we look at machine learning from the statistical standpoint, we can assume that we have a joint distribution over the input space and the output space, and we show that using this pxy. And we use these two together in this subscript to show that this is the joint distribution. Also, we know that our machine learning model is in the form of a function f that accepts two types of inputs. And why is that? So x here is our inputs or our features. So in the case of the regression problem we just saw, this is the years of experience. So we want to be able to provide any number of or years of experience and be able to find the output. But this function f is not completely defined because we have to train or learn that. And those parameters that we have to learn, we show them using theta. So these theta are parameters that we have to infer or learn. So one way to think about this is that in the simplest case where we have linear regression, here we have x, here we have y. So this line has two important parameters, and I can just summarize them using theta. One is a slope and the other one intercept. So once I figure out what this theta is, or here better say that what the theta parameters are, since there are technically two of them, then for any x, I can find the corresponding y value. But the key thing is we need to first find this. And therefore, I can show the output of this function as f of x semicolon theta. And this is just to ensure that x and theta should not be treated equally. And theta is actually the unknown that we want to learn through the training process. So given this, now in order to find theta, we have to form something known as population risk. So the way this works, we assume that we have a loss function L that measures the difference between the actual output. So the actual output comes from your training data and what you predict. And what we predict is this function f that we have. And ideally, you want to be able to minimize the expected value of these input-output pairs coming from this joint distribution. And remember, here x and y are what we are finding the expected value with respect to, and therefore this is indeed a function of theta. So this is what is known as population risk in the statistical literature. So we have a loss function L. Let me add this here. That measures the difference between Y, the actual output, and the predicted output. And then ideally, we want to find this expected value over XY pairs using this joint distribution. And this gives us the function of theta, and we want to be able to minimize that as much as possible. But here is a problem, which is a big problem, that we do not know the joint distribution between x and y. So if we really know this joint distribution, we probably don't even need to solve this machine learning problem here because we already know how x and y are related. For example, the joint distribution can be a multivariate normal distribution with a known covariance matrix and everything that we need to know. However, that's something that we have to take into consideration that we don't know the relationship between input space and the output space. So therefore, we have to approximate this. And that's a very simple idea that we know from statistics. If we have population mean, and we don't know what that is, we can approximate it using the sample mean, right? So this means that in this case, we do not really know this joint distribution, but we can find the sample mean, which means that now for n equals 1 to n is the sample size, we are going to compare each predicted value for xn with respect to the actual output or ground truth output that we have in our data set. And we show this usually using L of theta. So this is what is known as empirical risk. And therefore, in general, as you have more data points or the sample size increases, you get better and better approximations of population risk. Therefore, in general, if you have a data set with a large number of samples, that's more ideal. However, the reality is that in many cases, you have a limited number of data points because of the labeling constraints and everything else that we discussed before when we talk about supervised versus unsupervised learning. Okay, so this is kind of like the summary of what we just discussed about population risk, loss function, and also empirical risk. And once we find the empirical risk, now we can form the empirical risk minimization problem, where the goal is to find the value of the theta that minimizes this empirical risk function. And this is very important because we are not really looking at the minimum value of L of theta. We are actually looking at arg min, which means that the value of theta that minimizes L of theta, right? We are looking for our solution, which means that what parameters are actually going to lead to the minimum value of this empirical risk. And by solving this optimization problem, we identify the model that best fits the training data, right? That's the simple idea behind training in machine learning models. Since we talked a little bit about classification problems, let's look at two different types of loss functions. One very, very simple loss function for binary classification problems, especially, is the 0-1 loss. So as the name suggests, means that this loss function is either 0 or 1. And we can show that using the indicator function of y not equal to y hat. So y hat is our predicted value. So recall that this is technically that function f that we have. And for now, let's just assume that that function is either, if it's a binary classification, 0 or 1. And the actual output is also 0 or 1. So if the ground truth or the true output is not equal to the predicted output, meaning that if this condition is true, then the indicator function is 1. And if this condition is false, which means that in that case, the true output is actually equal to the predicted output, then the value of this loss function is 0. So this is very intuitive, right? So anytime you make a mistake, the loss is, or the penalty to pay is 1. And if you make a correct prediction, there's no penalty. So it's 0. And therefore, in this case, this empirical risk that we have is technically the misclassification rate because you're dividing this sum by the total number of data points that you have. And this sum, because in most cases you have probably 0 when you make correct prediction and you get only 1 when you make an inaccurate prediction. And so this sum by itself is the number of times that you misclassified. And if you divide by that by the total number of data points, that's your misclassification rate. And obviously that's a good measure or loss function or empirical risk because it's always good to try to reduce your misclassification rate. However, a problem here is that this is really in a binary format, right? Meaning that either you make a correct prediction or not. It does not consider how bad your inaccurate prediction was. And therefore, there are other possibilities to take that into consideration. And one of those things is this thing known as hinge loss. So this is something that we're going to discuss more when we talk about support vector machines. But here the goal is just to show you, two examples of loss functions to see how different they can be. So something also I need to mention, and I forgot, is that when you talk about loss functions and finding this empirical risk, it is very important that loss functions to be non-negative, because if they can take on negative values, then positive and negative values can cancel. And therefore, it's not a really good idea to have loss functions that can be negative. That's something you should always avoid and make sure that if you make a mistake in terms of your prediction, then at least there should be something that is non-negative penalty to pay for that mistake. Otherwise, positive and negative errors, they will cancel each other. And you can easily see that this is something that we satisfy using this hinge loss function. It's max of 0 and 1 minus y times y hat. So this means that if this second term, 1 minus y times y hat, is negative, then the maximum is 0. And if 1 minus y hat is greater than 0, then that would be the maximum value. So there's no way we can return a negative value using this function. And in this case, to explain this more, we have to make a few changes to what just explained before. So in this case, we assume that the true outputs or the labels that we have for the ground truth data points that we have in our training data set are either -1 or +1. and you see y. So the key thing here is that actually the reason that we multiply this y times y hat is because y, it's kind of like a sine function, can take -1 or +1. And y hat here is actually the output of machine learning model. And interestingly, in this case, y hat should not even be discrete. It can be a continuous score, or what we call it later as margin. And so how does this then work in terms of this loss function? So the idea is very simple. If y times y hat, right? So y, remember, is either -1 or +1. Y hat is a continuous number. If this multiplication is greater than or equal to 1, then 1 minus, let's say, 2 is -1. So this means that this number here is negative. So the maximum is always this 0 value. So this means that there's no penalty to pay because we have our loss function here is equal to 0. However, if y times y hat is less than 1, let's say it's 0, then you can see that here we get 1 minus 0, which is 1, and that's the output or the result of our loss function. And in that case, obviously there is a penalty to pay, and you can see that this loss increases linearly as this predicted value y hat or f of x and theta, that's just something we use here interchangeably, deviates from the classification boundary that we have. So of course, we're going to explain this later in more details, but here we have enough to understand what this loss function is. And in fact, since we can use Python in this course, you can really see very well how this loss function looks like. So we don't have to necessarily solve this problem by hand, and we can embrace code to solidify our mathematical understanding. So let's just review what we have. So we know that our labels are binary, so either -1 or +1. Since we have a Python code here, we have to make a decision here and decide whether our label is either -1 or +1. In this case, we assume that it's actually +1. And then this y hat, as I mentioned earlier, is a continuous score here. So it's a real value number. And if you want to use this with the 0, 1 loss, you can just simply look at its sign, meaning that if y hat is greater than 0, then the sign of this is +1. So the predicted class is +1. And if this y hat or predicted value is less than 0, the sign is -1. So with this, you can compare this predicted and the true outputs and use the 0, 1 loss that we had, right? So we have two possibilities for the true output, two possibilities for the predicted output. However, the nice thing is that with the hinge loss, we don't really have to use these binary situations because now we can actually consider the fact that this y hat is a real valued number. So we're going to discuss in the rest of this lecture, some libraries like NumPy and Matplotlib, which is for visualization. But here I just want to show you how easy it is to read this code, right? So both of these loss functions, they accept two input arguments, the true output that comes from your training data and what we predict. So np.where is basically saying that if y true times y pred, right, these two true and predicted values, if the multiplication is less than 0, then the uh, output is 1. And if not, the output is 0. And we can do this because, again, here, this y true is +1 or -1, right? So if in this case, our y true is 1, and that's something we're going to set later on, if our predicted is 1, then there's no penalty to pay. And in that case, the multiplication is greater than 0. But if the predicted value is -1, then -1 times 1 is -1. So this condition is satisfied, which means that there is a penalty of 1 to pay in that case. However, for the hinge loss, it's a little bit different. It's the maximum of 0 and 1 minus y true times y pred. And therefore, this is not just restricted to return 1 or 0. It can be, the output of this can be any real valued number. Now, to be able to plot this, so obviously our y true is 1 or -1. Here we assume that it's 1. And then for Y pred, I assume that it's somewhere from -2 to 2, and we use 500 equally spaced points between the two. So obviously you can choose any range you want here. If you want, for example, -4 to 4, or -10 to 10. But in this case, right now we have this, and you're more than welcome to experiment with the code. And everything should work here when you run this cell. And in this case, we're going to calculate the two losses, the 0, 1 loss and the hinge loss. And now we can plot on the x-axis this y-pred, this continuous score that comes from our machine learning model. And then on the y-axis, one time we plot the 0, 1 loss and the other time the hinge loss. We make sure that we use the right labels so that we can later on see differences. And here you can really see how this works. So obviously, when you have 0, 1 loss, as we mentioned, y true here is 1. So this means that if the predicted value is greater than 0, then there's no penalty to pay, right? Because then the predicted value is also 1, and so there's no penalty to pay. But if there is a negative value, then the predicted label is technically -1 because it's the sign of y pred. And in that case, we have to pay this penalty of 1. However, you can see that with the hinge loss, it's a little bit different in a sense that if y times y hat is greater than 1, right? So from 1 to the right, there's no penalty to pay. If y times y hat is 0, then the penalty to pay is 1 minus 0, which is 1. And that's what we see here. And then as we actually get further and further to the left side, you can see that this value of the loss function actually linearly increases with y pred. So this means that now we are actually sensitive to how far y pred is. So with this motivation in place, now we can talk about the general workflow for machine learning models. So the idea is that we always start with our inputs or features, which we show them using X. And then we send them through some data transformation layers. For example, if it's a linear regression, this is typically one layer, but in more complex models like neural networks, we have multiple layers. And since we are working with parametric models so far, so this means that each data transformation has its own weights or parameters that we have to find. But however, for now, let's say we have some initial guess about what those things are. So this means that we send our X into these data transformations until we get some predicted outputs. This can be, for example, 0, 1 for the simplest form of binary classification, or a continuous score as we saw in the hinge loss. And then we know the expected outputs too. So this is, if it's supervised, means that it's the true outputs that comes from your training data. Remember, your training data is input output pairs. However, since also I want to make sure that we focus on other types of learning paradigms, this can be also something that we have in unsupervised learning, that in that case is not necessarily the true or actual outputs, but it's what we expect to be the outputs. That's why I use the term expected. And now, given these two, we send them to a loss function, also known as a cost function. And this measures the difference between the two, for example, using 0, 1 loss or a hinge loss. And based on this, we form the empirical risk minimization problem, right? So in that case, we have to find an optimizer to find the optimal solution for these weights and parameters. And this means that then we know how to transform the input features so that these predicted outputs are as close as possible to expected outputs. This general workflow is something that we use throughout the course almost all the time, and that's why it is really important to have this picture in mind, whether it's something as simple as linear regression or something as complex as deep learning models. The general workflow is very much the same. And then the final thing I want to also mention here is about the idea of generalization. So recall that in machine learning, right, when we form this empirical risk, we form this average value of loss on some training data points. And the key thing is that, well, if the goal is just to find, the best model for the training data, we can always memorize the data, meaning that we can just, draw a table where we have inputs and the corresponding outputs. And in that case, we can always make 100% accurate predictions. But the goal is to find generalizable rules or patterns, and therefore we always need to also have some testing data where we can measure these empirical risk for the testing data as well. And these two should be comparable. And if in some cases you see that this empirical risk computed using the test data is significantly higher than the training data, that's not a good sign because this means that your model is overfitting